So today we'll be discussing how the error, approximation error, is always perpendicular to the basis vector, and then we will derive the matrix vector equation for multilinear regression. So before starting this, let's go to one note. Over here we'll discuss everything. So for example, let's take any vector called v. Okay, now we need to take an approximation of this vector with respect to a basis vector. Okay, so for example, this is a basis vector called u. Okay, and you can make it larger or smaller. For example, the basis vector is smaller. Now let me draw this again. This is a vector v. This is the basis vector u. Okay, if you want to make it larger, you can take multiply this with an vector with a scalar quantity which is c1. Take c1 over here and u. Okay, now this is our vector, basis vector. This is the basis vector. Okay, and this is the error, the difference between the main vector and the basis vector. Okay, the vector v, and this it will denoted by e bar. So e bar is defined as the difference between v vector and the basis vector c1 u bar. Okay, now you can see over here, this is perpendicular to the basis vector. Okay, the error, approximation error, which we have taken is always perpendicular to the basis vector. To derive this, I will take two cases. For example, take this basis vector. Okay, and this is the vector v. For example, the basis vector, this is the c1 u1, this is the vector basis vector. For example, the error is not making 90 degree. For example, it's making something around some obtuse angle more than 90 degree. In this case what happens, the basis vector will be more. Okay, it will be longer than required. Okay, see, it's longer. If the error approximation error makes any acute angle with the basis vector, in this case it will be shorter. Okay, this is c1 in this case, c1 u1 in this case, it is shorter over here. But if it makes more than 90 degree, the error approximation error with the basis vector, it will be more than required. Okay, so if the error approximation error gets more than 90 degree or less than 90 degree, apart from 90 degree, apart from perpendicular to the basis vector, it will going to make, it will be the the basis vector, it will be sometimes more than required, length will be more, and sometimes the length will be less. So it has to make, always it has to make perpendicular, it has to be perpendicular with this the basis vector. So we found out, like, the error vector is always perpendicular to the basis vector. Okay, this is the basic principle. In this case only, it will going to make the perfect length, and you will get the least error between these two things. So this is the rule. After this, I will go into matrix vector equation. We'll derive this derivation of matrix vector equation. Okay, so for example, let's take three quadrants. Okay, three axes, this is z axis, this is x axis, this is, for example, y axis, xy, the g axis. Okay, let's take any vector in the space. For example, let's take v only. Okay, now if you see here, if you want to make an approximation with respect to a base vector, and as there are three coordinates are here, we'll take two base vectors with respect to x and y, or something else, like you can take the vector, base vector as phi1, this is the phi1, and another base vector as phi2. Okay, this is phi1, this is phi2, and let's make an plane using these two vectors. Means these two vectors will lie on this plane. Let's change the color to visualize this properly. This is phi1, this is the phi2, and this is the plane where the phi1 and phi2 lies. Okay, this is the plane where phi1 and phi2 lies. Here, if you see, as you already told this thing, that the error, whatever it is, the error, the approximation error, will always be perpendicular to the basis vector. So let's draw the error over here. Let's get back to our black color. See, this is the error, and this will be perpendicular. Okay, let's draw it properly. This will be always perpendicular to the basis vector, and means this is plane, the basis vectors, both the basis vector lies on this plane, so the error will be perpendicular this way to this plane. Let's say this plane is defined by c1 phi1 plus c2 phi2, any two coefficients. Okay, c1 phi1 and c2 phi2. Then we can say this. Okay, this is c1 phi1 and c2 phi2. So we can say this, as I have already told, the error approximation, or the error, is always equal to the main vector v minus the basis vectors. Okay, the basis vectors over here are c1 phi1 plus c2 phi2. Okay, so let's take this, as equation 1. Okay, this will be used. Okay, now as we know, the error will always be perpendicular to the basis vectors. Okay, so here we can deduce that error is perpendicular to phi1, perpendicular to phi1 and phi2. Okay, let's take the first case. Error is perpendicular to phi1. So what you can say, we know the dot product. So dot product means whenever we take dot product of two vectors which are perpendicular to each other, they will get, it will be get 0, because see, dot product means what, like for example a and b are there, dot product of a vector and b vector, and both are perpendicular to each other. So it's defined by a, mod of a, magnitude of a, magnitude of b vector multiplied by cos theta, and the angle between them is 90 degree. So cos 90 becomes 0, so it will be 0. Okay, using this rule we can take, say like this, e dot phi1 is equal to 0. Okay, now putting the value of e over here from this equation 1, what you will get, phi1 dot vector v minus c1 phi1 plus c2 phi2. Got it? It will be equal to 0. Okay, so if we take the dot product inside to this bracket, it will come like this, phi1 dot v minus, if you take the minus sign to this side, it will become phi1 dot c1 phi1 plus c2 phi2. Okay, if you expand this even more, phi1 dot v vector, it will be how much, like phi1 dot product of phi1 into c1. C1 is just scalar, so you can take it to the side. It's just like a number, so you don't have to put it inside the dot product. And similarly, phi1 dot phi2 into c2. Okay, and one more thing I would like to say over here, dot product we can also take like this. See, dot product means multiplication of two numbers. Means if you multiply the same number, multiply the same vector with same vector. So I'm telling this, see, this is the a vector. Okay, if you take dot product with itself, it will come like this: a magnitude of a to magnitude of a cos, and the angle between the same vector will be 0. Means a will making 0 angle with itself, so it will be 0, and cos 0 is 1, so it will become a square. Okay, and this thing can also be written as, see, also be written as a transpose. For example, it's a matrix. If you take it as a matrix form, a transpose into a, it can be written as this also. So we can use this here to get phi transpose v vector, its transpose, is equal to phi1 transpose phi1 c1 plus phi1 transpose phi2 c2. Okay, so let's derive this. Like, let's take it in the matrix form. It will get phi transpose. Okay, it's transpose. Let's take the values of phi1 over here, so we have transposed it, so the rows become columns. For example, they were in rows, it will be become in columns. So we will get phi1 values like this, multiplied by this row vector v, get values like this. V is equal to, again, phi1 phi1 multiplied by, no, phi1 phi2 is there, so you can take this. These are the column vectors, so you can add them together. Phi1 phi2 and c1 c2 will be as in columns. Okay, so if you take this to the other side, I will explain you how it happens. So see, if you do the metric column, metric multiplication over here, if you do the metric multiplication over here, see, this is the phi1. Okay, this is the phi1, this is the phi1 matrix. The phi1 matrix will get multiplied with and in the matrix multiplication we do row into column, we multiply the row with the columns. Okay, so it will become, see, the row will multiplied with the column. Okay, again the row will multiplied with the column. Okay, so over here, if you see, if you multiply, solve this thing, you will get the exact this equation. So let me show you how it happens. Phi1 multiplied by phi1. Okay, so we'll get this. Similarly, phi1 multiplied by phi2. Okay, we'll get this. Okay, let me show you how it happens. Here, this for example, there are n values. Okay, n values of phi1, and you can see, you can write the dimension of this matrix over here. Rows, how many rows are there? One row. And how many columns are there? For example, n columns are there, n quantities are there of phi1, so n. Here as well, how many rows are there? Here two rows are there. How many rows? 1 2 3 4 5 6, n things will be there. See, for example, 1 2 3 4 5 6, and n quantities are there. Okay, so this is the first row. Similarly, again here as well, this is the first row, this is the second row, this is the third row, and similarly you will get how many rows? N rows. And how many columns? 1 2, two columns. Okay, here you will getting how many rows? Two rows and two columns only. So you will multiply, if the for the dimension matrix multiplication, the rows of the first column, columns of the first column should be equal to the rows of this sorry, to multiply two matrices, we have to the the dimension of the first matrix, means the rows, columns of the first matrix should be equal to the rows of the second matrix. You got my point? Like I'm saying, the columns, means here this thing has to be equal with the the rows of the second matrix, means the columns of first matrix has to be equal with the rows of the second matrix. Then you can do the matrix multiplication, and once you do this, you will get these two numbers, means the rows of the first matrix multiplied by the columns of second matrix. Okay, so we'll get like this, phi 1 into phi 1, we'll get over this, something we will get over is phi 1 into phi 1 here we will get. Okay, then phi 1 into phi 2 will get over here, phi 1 into phi 2, sorry, phi 1 into phi 2 will get over here. Okay, now it will become 1 cross 2, means 1 row 2 columns, there is 1 row and 2 columns. We will multiply with this c1 and c2. Here the dimension of the coefficient matrix is 2 cross 2. Okay, so here you will get, see, these two are equal, so you can do the matrix multiplication and you will get row into column. So we'll get a matrix of 1 cross 2, and here it will be phi 1 into phi 1 c1 plus phi 1 phi 2 c2. See, we got the same equation again which we had here. Okay, phi 1 into phi 1 c1 plus phi 1 phi 2 c2. Okay, so it is the same thing as this. Okay, now let me derive this even more. This thing you need, this thing is important, so let me take this from here. Let me try if you'll be able to take it or not. This thing, okay, it's not possible to do it. Let me write it again. I will write it again over here. I will just need to explain something. So I'm just writing this over here. Here we got this one, we got for our phi 1. Okay, this was the phi 1, no, it is the phi 1. Okay, this matrix made up of phi 1 and phi 2. Phi 1 phi 2, then c1 c2 the coefficient matrix, then again transpose of phi 1, and then again the vector. Okay, the matrix of this vector. So this we got for for E means the error dot phi 1. Solving this we got this. Similarly, if you solve for this one for the phi 1, you solve for this, you will get again similarly it will become phi 2, and these two will remain same. And other everything will be remaining same, c1 c2, and again here it will become phi 2, and this is the vector. Okay, got it? Now moving forward, if you combine these two things together, what will happen if you combine this one and this one together? We'll just concatenate these two things, the rows into columns, because they are, if you just multiply them and add them, it will be same. Okay, so if you just add two equations, these two things. Okay, if you see, you got this equation. Okay, if you add the second equation. If you solve that thing, you will get only, instead of phi 1 you will get phi 2. If you add those two things, it will become, you know, you will get the same thing. I will explain it later. Like, let me add them together. So it becomes phi 1 phi 2, and it will remain same, phi 1 phi 2. This will remain same, c1 c2, and again here phi 1 phi 1 phi 2, and this is will be the vector. Okay, got it. Now if you see, if you do the matrix multiplication over here, what you will get, phi 1 into phi 1. Okay, then this is the first column, first row, then phi 1 plus phi 1 into phi 2, then again phi 2 phi 1 phi 2 phi 2. It will be equal as this. If you add these two equations now with phi 1 and phi 2, you will get the same thing as this. Okay, so this thing over here is called, it was the transpose of this. You can see over here, this and this are almost similar, and apart from these are the transport of this. The rows become columns over here and columns become rows over here. So this thing is called our design matrix. Okay, this is called let's take this A, it's called design matrix. Okay, and using this you can solve for the values of c1 and c2, and once you get the values of c1 and c2, you can easily get the value of, you know, this basis vector. Okay, by putting the values of c1 and c2 over here. So in this way we solve this equation. So let's take an example and I will show you how it happens. For make it simpler, like you can write like this: transpose of a matrix, means design matrix, into design matrix, and the coefficient matrix you will write over here is the coefficient matrix, equal to transpose of design matrix into the vector. Okay, this is the rule. Okay, so let's take an example. I will use it, plot the graph, and use this matrix vector equation. I will going to solve for the coefficient. Okay, so here let's take an example, simple example. Y equal to x square plus sin x. Okay, I'm taking this example just for example. Okay, so here to make the design matrix, what we'll do, we'll take the coefficient of x and x, you know, sin x. Okay, x square sin x. Okay, for example, there are numerous values. These are c1 c2 take for coefficients. Okay, and the coefficients will come like this: c1 c2, and it will be the y vector. If you see, if you multiply these two, you will get x square into c1 plus sin x into c2 is equal to y. Okay, you got this equation. So we'll use this only to get the answer. What we'll do, we will, for example, there are n values of y, n values of y and x. Okay, taking n values are there. So for example, there are many values you can take like this. Okay, so I'm going forward. This is our design matrix. Take this as A. For different values of x, you will get different values. So for example, let's put, for 1 you will get, for 1 you will get 1, and sin 1 is something, some value you will get. Okay, for 2 you will get something, 4 you will get something. So there will be n values. Okay, so it will be an 2 by n matrix, 2 rows, n n rows, n by 2 matrix, n rows, n rows and 2 columns, and here it will be 2 rows 2 columns, and these are n rows and 1 column. Okay, and to solve this, if you see, I'll tell you an interesting thing over here. If you multiply this, if you do the multiplication, matrix multiplication here, x square, okay, 1 into this thing, 1 into 0.5 or something, for example 0.5 or something, 1 into 0.5 c1 plus 0.5 c2 is equal to some value y1 you can take. Okay, so again those things. So here you can see there are two unknowns, but we'll get n equations. See, this is the first equation, we'll get first equation, and you will do the second multiplication, will do the second equation, and we are getting for two unknowns, we're getting n equations. Okay, but we need two equations only. So to solve it, we'll multiply this method only. So, okay, we will multiply the transpose of the design matrix in the both side. So I will put transpose of this over here. Now x square sin x, values will be over here, and again this will be x square sin x, the values will be over here. c1 c2 is equal to y1. Okay, we need to multiply the matrix, the design matrix, transpose of design matrix over here. So we'll put this here, this transpose of design matrix, x square sin x, like this, and y values will be here. Okay, y1 to y. Now we'll see, if we solve this, this will be 2 into n, and this will be n into 2. Okay, as you did the transpose, in the transpose you will get the rows will change to columns, and if you just multiply this, you will get a vector, a matrix of 2 by 2. Okay, 2 by 2 matrix you will get, multiplied by c1 c2. And here also you see n cross 1 was there, is 2 cross n is there. Okay, if you multiply this, you will get a matrix of 2 cross 1. Similarly 2 cross 2. Okay, yeah, that's right. Okay, 2 cross 2, 2 cross 1 is here. Okay, I got confused. Okay, two rows are there, one column is there, so 2 cross 1. So if you multiply this, you will get a matrix of 2 cross 1 with the coefficient of c1. For example, some value will be there, a b c something, is also a something. So again a b c or something, c2, some matrix, I'm saying some scalar quantity, the value you will get into c1. Here you will get y1 and y2. Okay, so we got two equations and two unknowns. So we get solving this, you will get the values of c1 over here, we will get the values of c1 and c2. Okay, so let's go and start the coding thing. We'll go to collaboratory. Here what is our equation? It is cx c1 x square c2 sin x. Okay, so let's go here. Okay, make a new notebook. Okay, so before beginning we need the numpy module, so we'll import that. Import numpy as np. Then we need plotly to plot the graphs, plot the graphs, everything, and for that we will import from plotly dot make plotly dot subplots will import make subplots. Okay, shift enter. Okay, then we will take the values of x, np dot linspace. Over here we'll take the values from minimum value and maximum value. So we'll take -1, the minimum value of x, and maximum value is 1. And how many points you want within -1 to 1? Let's take 50 points. Okay, then y is equal to, we have that equation, we'll put that equation over here, and our equation was c1x square plus c2 sin x. Okay, I will put x square, no need to put c1 c2 over here, c1 x square and x square plus sin x, we need to take np dot sin x. Okay, that's done. Okay, there is an error over here. Okay, we need to put normal brackets. I did put square brackets, that it didn't work. The syntax is for normal brackets, so okay, it's good now. Now we'll do, we've taken the data, now let's plot the data. Okay, okay, we need to design that matrix. We need to put the design matrix. For design matrix we need x square and sin x. Okay, x square and sin x. So design matrix, it was a, let's take as a design matrix. Then we'll put np dot c. Okay, it will concatenate all the values of x. Okay, for so I will show you how it happens. First value is x square, comma, then np dot sin x. Okay, so what it will do, it will, okay, what's the error over here? Okay, import np as numpy. A equal to np dot c coordinate. Okay, I need to put these brackets, I'm making mistakes over and over again. Here x square, then sin x. Okay, now it will run. Should run. Okay, completely, I think I forgot the syntax. Np dot, yeah, it's right only. A is equal to np dot c x square, comma, and np dot sin x. Okay, it came. I think some issues was there. Okay, no problem. So we got our design matrix. Now we need the coefficient values. Okay, for that we need to solve it, and to solve it we have to solve this thing. Okay, this equation, and there is a function to solve that. We can directly do c, whatever values you'll get, you'll put it in c. C is equal to np dot lin alg dot solve. Will give the the equations it will solve. Okay, so what do we need first? See, where is our equation? Okay, see transport of design matrix dot the design matrix, and transport of the design matrix dot the vector. Okay, so here the vector is 1, so we will do like this. A dot t means you taken the transpose of that. Here at the rate is our vector multiplication sign into a. Then the second thing is a dot t means the transpose of design matrix multiplied by y vector. Okay, shift enter, linear algebra. Okay, I made mistake over here. Yeah, okay, shift value is stored. Now if you want to see the value of c's, means our coefficient matrix, we will print c to see the values. Okay, it's 1 and 1. Okay, we got these values. Now let's go and plot it. To plot it, we'll call fig equal to makes plots, then fig dot add scatter, x is equal to x, y is equal to y, then mode is equal to markers, then fig dot add scatter, x is equal to x. Here y is equal to c. We already got the values of c, and using these values of c we can get this value. See, we got the values of c over here. Okay, and if you multiplied the design matrix with the the coefficient matrix, you will get the values of y. Okay, this which we have calculated. Okay, so we'll see y is equal to a dot multiplied by the coefficient matrix. Okay, and here the mode will be lines, means the value we have calculated. This it will give the x and y values according to the equation. It will solve. You will just put the value over here and calculate the value of y and plot it, and this we have given. Okay, we calculated the values of x. This is our approximation. We'll see how it how come it comes closer to the real value. Okay, just to make it bit more aesthetic, we will put update layout. Your width is equal to 600. Let's take 900 or 800. 800 would be better. 800. Height is equal to it will be something around 500, and template will be plotly dark. Okay, shift enter. Okay, is there any issue here? Figure that scatter. Okay, I made. Okay. Oh, so Python is a case sensitive language, so if you make some errors like a small case, okay, you can see you got a perfect fit. Over here. So the values you have calculated for the C matrix, means the approximation was it came into a perfect fit. If you want to get some noise over here, you can take some noise like C y is equal to np dot random dot normal local is equal to y, scale is our what you call scale is our standard deviation. Let's take it 0.5 or something, and okay, we got too much. Okay, we got too much noise. Let's take it 0.1 only. Oh, still too much. 0.5 or something. 0.05. Okay, it looks good now. Still too much noise. Let's take 0.1. Yeah, it looks good now. See, you got the perfect fit. And this was it for the first part. Thank you.